Hello everybody. So today we will be going over a program that I've been working on for about the past month or so. And so this is going to be a Python program here that was inspired based on my previous programs with database operations, database management systems specifically in different programming languages. So as many of you may not know, assembly, specifically the MIPS architecture using the Mars simulator, does not have database operations in the way that, say, Python or Haskell, etc. have. And so to do so, I decided to create a custom MIPS assembler with additional instruction mnemonics programmed in to perform said database operations. So today we're going to be going over some of what was done over the past month with this program. So I'm going to start off with a couple of notes real quick. So first off, the functions for the most part handle just like the real MIPS instructions, though there are some things that are not present in MIPS or Mars, which include specifically the certain instructions have not been added in, such as the double instructions, which I just didn't need, and a couple of syscalls, which are not needed since doubles are not in there. And then also when placing register operands, you need to use a comma to delineate because using just a space will cause issues. And also right here I have a list of the database operation functions, which are not going to work if you try to use them in MIPS or Mars. They are specifically programmed for this project, which is for fun. And they do kind of run in a similar style to how MIPS and Mars would have handled it if they could. So let's get into it. So, database connect. dbct is the mnemonic, taking in a register for the connection and a register for the cursor, as well as a register containing the address of the file location as a string. This is all built in through SQLite, so basically everything, the database will be as a file, not a server. So as you can see here, the database test.db is the file, which is tied to this program up here, database test.asm. This is a assembly file that I've written specifically to demo these database operations for this video. The rest of these files you see on the left-hand side here are specifically tied to whenever I was learning assembly a while ago, before taking a class in college requiring me to learn it, as well as these three, which are actual assignments given to me while learning it. So then database close takes the register for the connection and the register for the cursor and closes them. Database table / create view / modify / delete takes the connection register, cursor register, the address of the query that you wish to execute, so the create table if not exists, etc. Query as an address. Then the database insert with the mnemonic dbi takes the connection and cursor registers, as well as the query address, followed by the parameters used in the query after, which can throw an exception if there are too few or too many or even incorrect data types to check. So for instance, don't put a floating point register for something that is like a string result. Use a general purpose for that. Database update dbu takes the connection and cursor as registers, as well as the query, followed by the parameters used in the query after, again throwing exceptions. Database delete, or dbd, is about the same thing, deletes the rows from the database. This isn't to drop a table or a database, so you would use dbt for that sort of thing. dbd is to delete rows from the database, wherein we have the parameters of a register for the connection and cursor, and then the address of the query, followed by the parameters used in the query. Then we have database select, which is paired with dbit, or database iterate. This is meant to be iterate. And so database select performs the select query, and then database iterate iterates through the rows. So you select you have the number of the rows returned. So a register that stores the leftmost operand stores the number of rows you get from your select query. The cursor, the second parameter is your cursor register. The third is your query address, followed by all the parameters used within the query. Database iterate has the current row. So this is what you use to iterate through your rows. It's like a row number. Then the cursor as a register, followed by the correct number and type of registers of the attributes. So for instance, a string goes into a general purpose, int into general purpose, and a float into a floating point register. So let's get into the actual program itself. So first off, we've got to select a assembly file and open its handle so we can actually read all of the data from it. Obviously, we're selecting from the files within this assembly files program folder here. And so we use this function here, which just returns the actual open path once you've selected it as a read. And then we create or attempt to create a program object. Creating this program object will check the syntax of the program line by line and effectively create the program almost as an executable in a way. And if there's any errors thrown, syntax errors, etc., it'll kick you out and end the program prematurely, as in the assembly program becomes invalid. Otherwise, if you successfully create your program object, then you can run the assembly program. The reason we return this as a boolean is if you do not call syscall code10 at the end of your program, it gets this message dropped off bottom. There was no official exit. And so if you exit, you get a true, which doesn't call that. Obviously, if you get a runtime error, we will exit at that moment and end the program early. So what's actually going on behind the scenes with this program object? So we create this program object and it has this file. We're going to then call the assembler and then close the file. So calling the assembler, which is this whole function here, will divide your lines into some categories. One includes the text segment and the data segment. The text segment is where all of the lines, the actual instructions are for the program, and the data segment is where all the memory addresses are located. So if I were to say pull up this hello world ASM file, the text segment highlighted here is the instructions being executed, where the .text is the label that tells you, hey, we're in the instruction segment. Main telling you, hey, this is the main function. And then obviously you have the actual programming, so load immediate for, load the address of the variable name, syscall, print the greeting. Then load the exit code and exit. Pretty simple. And then data, we're just defining this in memory. But so the job of this is to find the data segment and text segment, define everything in there, and it will create two different types of lines, objects. So as you can see on the top here, we have a data line if we're in the data segment, and otherwise we have a line segment, or line if we're in the line, the .text segment. If we can't find the text segment, then the program is invalid. And this is for optimization purposes, to not have to, so to find certain pieces of data, I have to loop through the data line segment. So I create a list of data lines instead of just having them all as one big list of lines and or data lines. And then we have some helper functions here to help me find the text and data segments. And then we have the run assembly program, which is the function to run the actual program. We'll go over this in a moment. So let's go over what those line functions, or the line classes, plural, look like. So note that we are creating two different types. So this line handles the actual individual lines, which are the instruction lines. These are .text segment lines, which include .text and .global. They also include headers, such as the main function header that you saw, the segment labels. And then obviously so whenever you have any other thing that isn't that is an instruction, such as syscall or load immediate, and we need to check the instruction syntax. We have some helpers here to help with that, and then check instruction here. So for each function that I have programmed in MIPS into Python, we have to have a check for the instruction to make sure the syntax is correct. The actual mnemonic needs to be correct, and the number of params need to be correct, as well as the params themselves. So for syscall, there are no parameters. For something like add, there are 3 parameters, and the final parameter, since this is meant to be used similar to how the Mars simulator works, normally you cannot use immediates with just the pure add, but the Mars simulator allows it to be changed to add D or add immediate, and so this behavior is just programmed behind the scenes. Basically, you just call add, and it will act like addy if you have immediates. And then we have the stuff like jowl and subs, single precision. So like I mentioned, I have some of the single precision stuff implemented. I have none of the double stuff. And then we have the custom database related mnemonics here, dbct, dbcl, dbs, etc., which goes all the way to the bottom. And then we have the data line. This is the class used for the data segment, wherein we are storing the value, which is actually the hex of the memory address, the base memory specifically. And then the content type is like if it's a .asciz or a .float, .word, .space, etc. The content name is the name of the variable. And so note that we use this value here alongside the memory manager singleton class to locate in memory the actual value that's stored at that address. So all we're doing at the data line is really storing a memory address. We're not actually storing it here. And then we have a few helper functions to help find things. Then we have the register file. So as I was talking earlier, we had registers in MIPS and in assembly in general, and so we need a way to represent these. These are general purpose, and they need to be able to store things such as addresses, which are in hexadecimal, and they also have to be able to store stuff like integers when you load immediate, as well as the flop registers, which require you to be able to store floating point values in them. And so we have some general purpose ones like the return registers, the argument registers, temporary registers, save registers, the frame pointer, the stack pointer, the return address, the PC or program counter, which is just an integer storing the current instruction, which is actually used quite frequently when it comes to performing jump and branch operations, as all we have to do is change the PC to 1 plus the number of the branch we wish to jump to, and then obviously the flop registers, as well as the high and low registers used to store binary, and then the condition flag for coproc 1. We have a few helpers that I actually didn't use for this, but they're there. We have the classes for the registers to store the value and the name of the registers, and then we have probably one of the biggest changes I had to make while working on this was to actually model the memory of a computer behind the scenes, sort of. So this is a very simplified version of it. It's not exact. And so we have what is a singleton. So we have an internal implementation class of a singleton for this. So every single time we call an instance of this class, it will be the same instance. So the memory is always the same no matter how many times I create the instance. And so it just stores the most recent address, the actual memory dictionary, which controls the actual hexadecimal value, or the actual memory address and the value, the memory type, the memory availability, which is mostly regarding database memory. I will explain that in just a moment. And then the results of a select query, which is used later. So we have the add address, which allows us to add a new address to the dictionary or to the memory. And this is used whenever we are allocating memory from the data lines, when we are allocating memory using syscode call 9, which is a MIPS or a Mars implementation of the SBRK, similar to malloc and alloc from C, if anyone here is programmed in that. And then down here we have the database allocated memory segments. This is used for the select statements to store the data temporarily before we can in memory before we give it to the registers that you implement as parameters for your DBIT. And so we have some helper functions as well, like get address, get type, contains address, set all available, get first available, has available, and this one is no longer used, but memory dump, which was used to display everything that's stored in memory, including the address and the value. So now we're ready to run this program now that we've compiled it, or I guess assembled and linked it. So let's run the assembly program. So to do so, we set the register counter to the first line, and whenever we go in, we go through every line that's in there from top to bottom. We skip any of the lines that are an instance of the data line or none type. We skip empty instruction lines, and we skipped data lines. We don't want to see those. Then, based on what the instruction of that line is, which is stored as a variable, we call the function corresponding to it. So for syscall, we will call syscall and set the exit flag. For add, we call add. And for all of these, we add one to the PC unless it is a branch. So for instance here, branch if equal to 0. The branch, reason that we don't add afterwards is because we are going to set the actual PC manually in this function. So for instance, so we have all the functions here, so we just decide which one we call. We have a few helper functions before we get down there, so getting the register, getting the labels, getting the variables, etc. So now we have all the functions that actually represent the instructions. These are the functions that perform the tasks. So for instance here we have syscall. So for syscall, it'd be helpful if I don't press tab again. For syscall, what we do is we create a memory manager singleton, and depending on what code was in the VO or the argument or the VO here, we can do stuff like print the integer in the argument, print the float in the F12, print the string in argument, print the user input or get user input, get user float input, get string input. We can get allocation for more memory. This is the same as I mentioned with malloc and SPRK. And then the exit the program. Otherwise, you have a runtime error, your code is incorrect. And so we have all of these functions iterated or created down here that run these. A lot of the ones that have to do with, say, branching, which I could show here, say branch is equal. For this one, we need to get the jump to. So we get the line number. And then we get the values from the registers. If they are the same, we set the register to jump to. Otherwise, we just implement or we increment the program counter. So there's a lot of those that happen to exist in here. I'm not going to bore you with all the code that's within the program functions themselves because there is just so many of them. But I will also quickly show off the databasing one. So database connect. All we simply do is take those and create the database connection, close database connection. We perform the select here. We perform the insert here. We perform delete here. Database table, database update, and probably what was the hardest one to get working, at least on the side of programming it through assembly, was database update. And so I guess now we are ready to run some assembly programs. So let's start off with some basic ones. Let's start off with Hello World. All this program does is print Hello World to the screen and exit. So we run our program and we select our file. So Hello World is ID number 2. So we enter 2 and it assembles successfully Hello World, and then the program concludes. Now, let me show you what happens if you don't have the syscall written in here, right? So now we should get a dropped off bottom. So this is still number 2, concluded, but the program exit dropped off the bottom because we didn't exit code. Okay, so I'm going to go over a couple of these. So if statements. So this one will take a number input from the user, and if it is less than 100, print a message saying that it was less than 100. If the message is equal to 100, print a message saying it was equal to 100. And once again, if the input is greater than 100, print the message saying so. And so we put the number we were comparing to into the register, so we're going to compare S0 to all of our input. We get the user input by prompting them using syscall 5 to get the number into the temporary 0 and run the comparison. So set if greater than the 0 to 1, which means if the input was greater than 100, then set T1 to 0, or set T1 to true, which means 1 technically, and branch if equal to 0, which means we move down. Otherwise, we perform another check to check if it's less than, and then otherwise we run a check to see if it's equal to, and then it runs down here. So let's run if statement, which is key code number, or ID number 3. And so let's enter an integer value. Let's enter 10. So the number was less than 100. Let's try 103. Greater than 100. Let's try 100 on the dot. Boom. Nice. Now let's try, I'm not going to run all 4 of these, the addition, division, multiplication, subtraction. We're just going to use one of them because they all operate on the same principle. You're just prompting the user for an integer, reading the first integer, outputting what they got, output the number, prompt for another number, print it, read it, or rather read the integer, save it, output text, output that number, add the 2 registers, and then output the sum of the numbers and exit. And so number 4, enter an integer. So let's enter the integer 17. So we got the number 17 and then put it out. Enter another integer. So let's do 17 again. Actually, let's do 18 just to delineate it. So we get 35, prints the sum of them, and concluded. Thank you. Next up, label sections. So this one is where we started using more and more complicated functions within here. So what we do is we start off at text, we immediately jump to input. This probably could have just been removed and come into here sequentially, but that's fine. So we're going to prompt the user, so print the prompt and get the number. And then we're going to see what in the condition, then we go to the condition section, so we jump to here. And based on what they entered, we decide what to run. So if it was a 1, we add, a 2, we subtract, a 3, we multiply, a 4, we divide. And then we perform whatever operation. So we get our second and third inputs, so these are the inputs. We perform whatever operation, print the result, and print the result, the actual message, and then the result itself. And then at the end of each of these, we jump to the exit, which, as you could suspect, is just print message, exit code. This one is code 8. And so, since I showed off addition, let's show off subtraction. So we'll enter a 2 for that. Into the first number, let's do 21, and let's do 11, and we get 10. Sweet. Let's try multiple messages. So this one is just going to print 2 messages. So we have a message here, and then we have a message here, and then we have an exit here. Very simple program. These are in order from alphabetical, so that's why it's not necessarily in order of difficulty or anything like that. And so it just prints the 2 messages. Now let's skip past these 3 for now, because these get more complicated. We're going to do string input next. So we're going to print a prompt for a string. We're then going to read the string using syscall number 8. We're then going to output the text, output the number, or in this case, the number in question is actually just the input from the user. And so the reason that this is a bit strange is because you need to define the string size you're allowed to input and the container where the actual word is stored. And so the input here is where the data of the input from the user is being stored, the address of it. Right? See here, the load word is placing these in here. So we run string input, which is code 13. And we can enter a string like, I am so done with assembly. And it will print, I am so done with assembly. So let's try void procedures. So this one is just void functions being written. And so we jump and link to the first procedure, which is first. And we just print the first message. We then jump register, which means we come right back to here. And we print a message saying that we did the first message, the first procedure. So this message between calls. So we should see this is first procedure. And then between messages. Then we jump and link, go to the second procedure. We run it, so run the message and return. So we come back to this line, and then we sequentially run this line, so print the end message, this is after both procedures, and jump straight to the exit with the exit code. So this is code 14. And as you can see, first procedure, between calls, this is the second and last procedure, after both procedures ended. Finally, for the ones that I did on my own this is all before I took my assembly class, all of the ones I've shown up, including this one. This one is the while loop that I managed to have to create. And so to perform while loops, you just need to jump to a segment repeatedly. And so we enter the loop. This is the looped region, and we jump to input first. We prompt the user, get a number from them, check the condition. If their input was a 0, we go straight to the exit. Or if their input was a 5, we go straight to the exit, my bad. Otherwise, we go to the corresponding operation, which is add, sub, mult, and divide. And so we just perform the operation, and then we jump back to the loop. So within these, we just jump to the loop. And as you can see, for all of these, we just jump to the loop. So run it. This is code 15. Let's try multiplying this time. Let's do 4 and 5. We get 20. Now let's do division. So 4. Let's do 40 and 4. Got 10. Now let's enter 5 to exit. And now the code is done. Nice. Now let's start with the more complicated problems that I did back when I was in MIPS assembly the first time around for college. I haven't taken the second class on this yet. And so what we have here is the data segment here. And what this is meant to do is basically get the sum of numbers entered by a user. So we get an input from them. So enter a number. If the number is less than 0, then the loop is unnecessary. We just exit. If the number is equal to 0, it's unnecessary. We exit. If we did neither, then we sequentially start the loop. So we load immediate into T3. And we get the user input for the number we are adding to our total. Add it to the register we use to store as a sum using T2 to T0. Since the T2 has the input, we then decrement our counter, and if the counter is still above 0, we can keep running. At the end, we then just print the result and then exit. And so to run it, we use code 12. So let's do 5 numbers. So I'm going to enter numbers 1 through 5. And our answer is 15, as this is 6, this is 6, that's 12 plus 3 is 15. That's using Gaussian addition, for those interested. And then for PA3, so what this function does, or this program does, the first time you'll see me use global here, is it will get an array of integers and then tell you what the largest number in this array is. So we reserve a space for 50 integers, so because each integer takes up 4 bytes, which is considered a word in MIPS. And so we get an input from them. This is the number of numbers to put into the array, which needs to be less than 50. And then we loop through it, and we get the input from the user and add it to the array by using the store word command into our offset. When we're done, we then print the final print to get the final message. So we need to print this value using these, which is to find the max value within the array using a bunch of branches. So we run code 10, and let's do another array of 5. Let's do 10, 20, -20, 50, and 35. 50 is our greatest value that we entered. Finally, let's do this one, and then we'll get to the databasing one. So this program calculates 3 different things. 1, can calculate the Pell sequence number. 2, it can calculate a nth prime number, given that n is greater than 0, I believe. And it can calculate the square root of the approximate square root of a number. And so this one is the first time that I was exposed to using float point math in assembly. And so we start off by performing a Pell input. So we get, no matter what, we're going to get the Pell first. Then we're going to get the user's input to decide where we're going, whether that be the Pell, the prime, or the square root. And then we enter those header functions. We perform the operation for that and return back to user input. Or we go to user input. User input is right here, where all we do is print the main prop and get user input, integer input specifically, and then just return it wherever we're going. This is a function that we just reuse over and over again to get to save time on not having to call syscall 5 repeatedly. And so we do that for stuff like the square root call, which requires that we use the float point stuff. And then we obviously have the Pell up here and prime down here. So prime, and then I believe we have another thing for square root right here where we are loading from Coproc, getting the numbers, performing the square root loops, and then exiting. So I guess we'll go ahead and run this real quick. So code is 11. So Pell number, let's get the third Pell number. Let's get the nth prime number, so enter number 2. Let's get the 5th prime number, which is 11. Let's do that again and get the 4th prime number. That's 7. Let's get the approximate square root, so 3. So let's get the square root of 121, which is approximately 11. Note that this is done in floating point operations, so it's about as close as it can get. And let's enter 0 to quit. Sweet. So now for the fun part. I have a database and a database test program written here. And so before I display how this program works in assembly, I'm going to show you how this works in Python. Okay, so I wrote this, the database function, or the database program in assembly I'm going to show you. I wrote this Python program beforehand to display what it looks like if you wrote it in Python instead of assembly. And so the operations you'll see here are going to basically be the exact same you see in assembly. I basically copied this Python program but put it in assembly, and then wrote that assembly is run through Python because the assembly is now through Python. And so the main of this function just calls the connection, the tables, the insert, the update, the delete, the select, and the close, then exits, all in that order. And so simple connect, very simple table. Insert, you can insert student, class, or grade. Update, you can update a grade. Delete, you can delete a student, class, or grade. And select, you can select student by name ordered in by their name. Select class ordered by their name. Select the student based on their average grade, which is done through this view. Then you can select the class by their average grade, so that's done with this view. And you could select grades in a class, so you can select people's grades from here, except with their name and the class value. And then close and exit. I'm not going to show off this Python program. There isn't a need because I'm about to show you how it works in assembly instead. And so in assembly, let's take a look at get some database tabs up here real quick. I can close off a few of these tabs. Alright, so let's take a look at our database first. We have some names. We have some grades. We have some classes, which are mostly programming and math related. Some averages, class averages, and some single averages. These are the averages of a person within a class. So, for instance, this person, Jeff, here has a 99 average. If you go to grade, Jeff here is the ID number 10. And so 10, 10, 10 right here, 99, 98, and 100, that averages to a 99. So, what we have here are these are some messages used for exiting invalid input, space, period, and new line. We have some prompts used to get the IDs, the scores, the names, the outer prompt of a choice, and then the outer prompts themselves. We have the location of the database file, which is in DB, and I have this hard-coded to check the database's file or the folder for these functions. So all of your database files will be created and should be stored in this folder. These are the queries to create tables and views, the queries to perform inserts, the query to perform the update, deletes, the utilities to find the ID and names of students and classes, the select queries, storage for grade values, but this isn't just used when they're inputted by the user, these are also used when they are pulled from the DB. Storage for IDs when they're inputted, important float values such as 0, the array storage for the IDs of students and classes, the input for strings, which is used for names and classes, and then we start with our text segment. So the first thing we do in main is go to the connect function, and then we come back to this part, and then we run the tables, and then we come back. So quickly to go over what the connect and tables do, we're just loading the address of the database file, creating a cursor, or creating a connection, creating a cursor, and then inputting the address. Then we jump the register and return back to here, which then calls this. So for each database table that we create, database view as well, we load the address in all cases, and then we just call the create or dbt function or instruction with the connection, cursor, and query address. We then return with the jump register. Finally, we call insert outer. This takes us to the insert part of the function, or of the program. Note that after this, the subsequent layers of this are called in sequential. We don't jump and leak here, we just jump. So at the end of insert, we just jump straight to the update outer. At the end of update outer, delete outer, and then select outer. And then after select outer, we close and then exit sequentially. So let's look at insert outer. So insert outer is get a input from the user and then perform one of these operations. So input your student, class, or grade. Or if you entered a 0 to not repeat, then we go straight to the next segment of the main code, which is the update outer. And if we didn't have any of that, we perform an error message and send you back to the start of the loop. This is just the same as I do with my input validation in Python. You guys should be familiar with this. And so for each of these, insert student, class, grade, we have subcalls. So for student, we come here, class, we go down below, and below that is grade. And so we get the name from the user, so get the print, get the input name is now in T1, because we had to load the address, and then we perform the input, which is DBI, with the connection, cursor, query, and parameters followed behind it. Only parameter here is the name of the student, and then we go back to the outer loop to get another number to see what we're doing. The same is performed for the class, except we change what query we're using and the prompt. For the grade, we call a function to get the ID from the user of the student, and we save it and load the address. Then we get the class ID and do the same, save and load address. We then get the score, save it and load the address, and perform the insertion. So we load the address of the query, and we perform DB insert, with the connection, cursor, query, and then the 3 parameters. These parameters in order are the student ID, the class ID, and the score. So quickly to go over what we're doing in these functions, jump and link for the student ID and class ID, which are at the bottom. We come down here for student ID, and we perform a select query. So we get the utility statement, and we use this is the row counter. So after this is performed, the number of rows returned, so in this case 8 rows would be returned. 8 would be the number left in this register after this operation. We then pass in the cursor and the query. Afterwards would be any parameters, but we don't need any here, and then we iterate through it. For each iteration, which is performed by dbit, we pass in the current row number, the cursor, and then the IDs. So these are the actual parameters, these are the locations where the parameters end up. So the ID address, where ID is stored in memory, goes into T7, and the address of where the name ends up goes into T8. Afterwards, we load the ID into a register and save it into the array, the IDs array to be specific. We then print the ID, the period, the space, the name, and a new line. We then increment our counter and check to see if we repeat this loop. Now, then, afterwards, we need to see if that value given by the user is actually within the IDS array. And so right here is where we got the user input. We sequentially come into this function in IDs. And so basically if it's in here, good. If it's not, then we return to the top of student ID. So this right here will call an error, and it will loop if it If it reaches the end of the loop and hasn't found it, throw an error and have them re-input it. Otherwise, we go back to where we were. The class ID operates the exact same way. And then the score function just gets a floating point value from the user, and as long as that float value is greater than 0.0 or not negative, then it's considered valid. Otherwise, we'll just have it repeat. So once we've gotten through the insert segment, we are now in the update segment. So to perform an update, there are only two options. 0, we continue forward to the delete, or 1, we update a grade. And so when we update a grade, we get the ID and the class ID and the new score and perform the update using the db update with the connection, the cursor, the query, followed by the parameters in the order that we need them in. And so in this case, because of how this query was built, this query requires the score, then the two IDs in their order. Another thing to note here is that the way this query also works is you can alter the grade of a student that doesn't actually have a grade. So if I am in my student and if you were to select, I don't know, let's say you selected 11. You selected Lydia's ID. But Lydia does not have a grade for Python 13. Oh, nope, she does. Okay. She doesn't have a grade for C#, number 7. If you try to alter Lydia's grade for C#, a class she has not taken and does not have a grade for, then there will be no changes, but there will also be no errors because it is valid SQL. It is a valid SQL parameterized query. And so just keep that in mind, that you can change stuff that doesn't exist. It just won't change anything if it doesn't exist yet. So you perform that, and then we loop back. Then we go to the delete segment. And so we can delete student class grade, or we can skip to the select segment. And so you can delete a student given their ID, so we get the ID from the user, and perform the delete. Which is meant to be using dbd, by the way. These do all work using dbu, but dbd is the official way to do it. This is syntactically correct. dbu does the same function as dbu. The only difference is the naming convention, because on the back end, both of them are classified as execute non-query, I believe. So on class, you'll get the class ID, perform the delete, and on grade, you'll get the ID, the class ID, and the score, and perform the delete. Which, come to think of it, probably should just be these two. But if you read the query at the top, let's see, delete grade right here. So actually, no, this one isn't correct. Glad I caught that, actually. So this one right here is not correct. We actually don't need a score, and so all we really need to do to fix this is there. And so for this one, actually all you need to do is get the ID and class ID and perform delete with these two params here. Can't believe I missed something like that. That's insane. And then we jump to the select side. And so we have more selections for select than anything else, so I'm going to breeze through them. Once again, jump through them, otherwise we close. And so select, when you hit select, all we're doing is performing your query with DBS, and then iterating through all the rows and printing everything. Same thing for the name. And same thing for the student average, except for student average, we are using a float value here to store the float, and we are storing the name in T7. And the same thing goes for the class average, except instead it's now a name for the class and a score. Finally, for class grades, we need to get the class in question, so C#, Python, etc. Give me that ID, perform our select, and then print the student's name alongside their grade for that class. So everyone who has a grade for C# will have their name listed and their respective grade listed after the period. Afterwards, when you're done, it comes to the close function, calling dbcl or dbclose, given just the connection and cursor. And then we exit. Let's give this puppy a run. So we're going to start with the select statements because it's faster to show them off now rather than later. So for the rest of this demo, we're going to be using database test ASM. So code 1 for the rest of these. And so we're going to skip insert for now. We're going to skip update for now. We're going to skip delete for now. And so let's print the students listed by name. So here we have them listed by ID. I want to list them by name, so 1. And so now they are listed in alphabetic order. So from Abby down to Lydia. Sweet. Now let's list the classes by their name. Here we have them listed by ID. So let's try to get them listed by name. Number 2. And now they are printed by name. All the C's at the top. Now let's print the student by average grade. 3. These are coming from the single averages listed based off who has the highest score to the lowest score. Then we have the average grade in a class, so number 4. And so now, again, listed based off of who has the, or which class has the highest score. Game development was probably the easiest class on here. Okay, and then finally we have select grades in a class, so let's enter 5. And now we have to select the ID of a class, so let's select Python. So class ID 13. And so you see that Hunter and Lydia appear here. And if we go to grade, 13 for Lydia, or 13 for Hunter actually, right here, is 96. And then 13 here for Lydia is 95. Now let's exit the select, and now everything there is over. So let's show off some of the other functionality now that we've shown that this select works. So let's insert a student into this database. Let's say Greg. Greg is now in the database. So we reset. Greg is now here. Let's add a class to the database. We have to enter a class name. Let's add database management systems as a class. And so now DBMS is right here. Let's add a grade to Greg. So 13. Let's choose Greg. And let's give Greg a grade for database management systems, 18. Enter his score. Let's say Greg did a pretty good job, got an 85.75, relatively respectable grade in DBMS systems. And so now if I reset, Greg's score now shows up. So let's go ahead and skip insert, and let's try update. So we enter a 1 to update a grade. Now we choose a person to update a grade on. Let's say that we got Celeste's grade wrong. So number 12 would be the person we select. So there's Celeste. Now let's choose number 9. Let's say that her C++ grade was too low. So now we enter a new score for Celeste's C++ grade. Let's say she actually got an 89.64 or 63. Okay, now let's reset and see it changes. Let's get through update. Now let's try the delete statement. Let's delete a student. We're going to remove Greg here, just for simplicity's sake. So we choose someone to remove. 14 removes Greg. And so Greg is now gone, but because I have a query that allows this to delete, when I reset this, Greg's grades also disappear here. Pretty nifty. And also note that Celeste's grade updated and Lydia's grade updated, well, Celeste's grade updated whenever I reset because her other grade was changed. This is a very important thing with views. They're very nice for this. So now let's delete a class. Let's remove PHP. Actually, let's remove C. C is actually not taught at my school. Let's just remove C entirely. So now C is no longer taught. C is not in here anymore. It just appears. All grades related to C have just been cut entirely. And so now let's exit delete. Now let's check the select. Let's see what this looks like now. See, his grade went down by a little bit, I think. Let's try class by average grade. And let's try grades in a class again. And we're going to do 9. And you see this is actually Celeste's grade that we just updated. So, for those wondering, once again, this entire saga of me creating this was entirely inspired by not being able to do this in standard MIPS and wanting to do this myself. And so this roughly 3,100 line code program handles this. Again, caveats, there are no double instructions, and there are probably instructions I'm still missing, as my knowledge gap with assembly is a lot more present than compared to other languages. And so, like, the amount of knowledge that I'm missing when it comes to assembly is about on par with the amount of knowledge I'm missing for a language like Haskell or PHP, right? Other languages like Python, Java, C++, C#, I'm a lot more in tune with. I hope you guys found this video interesting or entertaining or got a kick out of this. For those interested, I may leave a repo somewhere for y'all to check out the code yourselves, maybe even write your own database ASM files. If y'all do, I'd actually be interested to see what y'all come up with. Peace.